Mathematical patterns. Introduction. In our daily lives, you have counted numbers between 1 to 10 with a journey of maths and life of mathematical patterns. In this chapter, we will learn about some of the basic concepts of maths that the chapter are mathematical patterns. You can execute the assignment to learn more about some of the contents of pattern. Are you ready? Let's dive in and learn how mathematical patterns works. Pattern. When some numbers or figures occur one after the other in such a way that we can predict to a large extent what would appear after any particular number or figure, we say that a pattern is formed. Examples 1. Consider the pattern 271927192. We can easily tell that what would appear next. Since the numbers 2, 7, 1 and 9 are repeated again and again, so 7 will appear after the last number 2. 2. Consider the following set of figures. All these figures together form a pattern in which the number of sides increases by 1 in each step. So, the last figure will be followed by a heptagon, a 7-sided figure as shown below. Number theory is the branch of mathematics that studies patterns in whole numbers. When some numbers are arranged in a definite order, according to a definite rule, such that we can predict which number would appear after any particular number, we say that the number sequence is formed. Some examples of number sequences are as follows: all ones, 1, 1, 1, 1, 1. Natural numbers, counting numbers, 1, 2, 3, 4, 5. Odd numbers, 1, 3, 5, 7, 9. Even numbers, 2, 4, 6, 8, 10. Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13. Triangular numbers, 1, 3, 6, 10, 15, 21. Square numbers, 1, 4, 9, 16, 25. Cube numbers, 1, 8 to 27, 64, 125. Powers of 2, 1, 2, 4, 8, 16, 32. Powers of 3, 1, 3, 9, 27, 81 to 43. Visualizing number sequences using pictures. Certain number sequences can be better understood through pictures and diagrams. 1. All ones. In this sequence, each term is equal to 1. Rule. The end term in the sequence of all ones is 1. Natural numbers or counting numbers. In this sequence, each term is obtained by adding 1 to the previous term. Rule. The end term in the sequence of natural numbers is n. 3. Odd numbers. It is a sequence of all odd numbers, numbers which are not divisible by 2, where the first term is 1 and every next term is obtained by adding 2 to the previous term. Rule. The end term in the sequence of odd numbers is 2n minus 1. So, the 10th term in this sequence is 2 into 10 minus 1 equals 19. 4. Even numbers. It is a sequence of all even numbers, numbers which are not divisible, numbers which are divisible by 2, where the first term is 2 and every next term is obtained by adding 2 to the previous term. Rule. The end term in the sequence of even numbers is 2n. So, the 15th term in this sequence is 2 into 15 equals 30. 5. Triangular numbers. It is a sequence of numbers which count the objects arranged in an equilateral triangle. Rule. The end term of this sequence is the sum of the first 10 natural numbers. So, the 8th term of the sequence equals to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 equals 4 into 9 equals 36. In general, the n term of the sequence of triangular number equals to 1 by 2 into n plus 1. 6. Squared numbers. It is a sequence of squares of natural numbers. Rule. The n term of this sequence equals to n square. For example, 10 term equals to 10 square equals to 100. Cube numbers. It is a sequence of cubes of natural numbers. obtained by multiplying a natural number by itself 3 times. 8. Hexagonal numbers. It is a sequence of numbers that count the number of dots arranged in a regular hexagons. The first term is 6, which gives the number of dots that join to form a hexagon. The subsequent terms are obtained by increasing one dot on each side of the hexagon in each step. 9. Hexagonal center numbers. It is a sequence of numbers that count the number of dots arranged to form overlapping regular hexagons. 10. Powers of 2. It is a sequence of numbers obtained by raising to the powers of different whole numbers. Recognizing patterns in different sequences. We shall now try to recognize the patterns in each of the sequences mentioned so far. This will help us find any unknown term of the sequence. All ones. 1, 1, 1, 1, 1. The same number 1 is repeated through this sequence. Natural numbers or counting numbers. Each term is obtained by adding 1 to the previous term. Odd numbers. This sequence contains of all odd numbers. The first term is 1 and each subsequent term is obtained by adding 2 to the previous term. Even number. This sequence consists of all even numbers. The first term is 2 and each subsequent term is obtained by adding 2 to the previous term. Fibonacci numbers. The first two terms are both 1 and each subsequent term is obtained by adding 2 terms just preceding it. For example, 6 term 8 is obtained by adding the 4th term 3 and 5th term 5. Triangular number, square number, cube numbers, powers of 2, powers of 3, hexagonal number, hexagonal center numbers. It's the same added. Relations among number sequences. We will now discuss how different number sequences are interrelated. 1. The sequence of odd numbers is 1, 3, 5, 7, 9. When we start adding these odd numbers from the beginning of the sequence, we can generate another sequence. 1, 4, 9, 16, 25, 36 and so on. We can recall that this new sequence 1, 4, 9, 16, 25, 36 so formed in a sequence of square numbers. It is clear from this picture that the sum of the first and odd numbers is n. So the first of the 10 odd numbers will be 10 square equals to 100 and the sum of the first 100 odd numbers equals to 100 square equals to 1000. That 10,000. 2. Let us study another number sequence. From the above calculations, it is clear that the sum of n counting numbers adding up and down is equal to n. Can you now calculate 1 plus 2 plus 3 plus 99 plus 100 plus 99 plus 3 plus 2 plus 1? Yes, this is a sum of 100 counting numbers adding up and down which equals 100, that is 10,000. 3. Consider a sequence of all ones, i.e. 1, 1, 1, 1. The new sequence of 10 on adding the terms of the sequence of all 1 is the sequence of natural numbers, that is 1, 2, 3, 4. Clearly, on adding the first 10 terms of the sequence of all ones, we get n. 4. Let's again write the sequence of all ones, i.e. 1, 1, 1, 1. What will if we add the terms of the sequence up and down? 1, 3, 5, 7 and so on. The new sequence obtained is 1, 3, 5, 7, which is the sequence of odd natural numbers. If we add the first 10 terms of the sequence of all ones up and down, we get the nth odd number 2n minus 1. Thus, the sum of the first 10 terms of all ones up and down is equal to the 10th odd number, which is 2 into 10 minus 1 equals 19. 5. The sequence of natural numbers is 1, 2, 3, 4, 5. Let's add these numbers from the beginning of the sequence. Please recall that the new sequence so formed, that is 1, 3, 6, 10, is the sequence of triangular number. We can depict this pictorially as shown below. Thus, the sum of the first 10 natural numbers equals to n triangular number equals to 1 by 2 into n plus 1. 6. Consider a sequence obtained by adding pairs of consecutive triangular numbers. The terms of this sequence are the squared numbers. We can depict this pictorially as shown below. The sequence of the powers of 2 is 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, i.e. 1, 2, 4, 8, 16, 32. What do we get when we start adding these terms from the beginning? 3, 7, 15, 31, 63 and so on. If we add 1 to each term of the new sequence 3, 7, 15, 31, 63, we get the sequence of the powers of 2 again. Thus, plus 1 equals 2n plus 1. Or we can say 2, 0 plus 2, 1 plus 2, 2 plus 2n plus equals to 2n plus 1 minus 1. From the above picture, we infer that the boxes from 1, 2 and 4 are next to the box for it. If the shaded box is added to these, they together perfectly fit into the box for it. Therefore, 1 plus 2 plus 4 plus 1 equals 8. Similarly, the boxes for 1, 2, 4 and 8 are just above the box for 16. These boxes together with the shaded box fit perfectly into the box for 16. Therefore, 1 plus 2 plus 4 plus 8 plus 1 equals 16. And in the same way, 1 plus 2 plus 4 plus 8 plus 16 plus 1 equals 32. 64, 128 and so on. We can generalize this result as shown below. 8. Consider the sequence of triangular numbers. That is 1, 3, 6, 10, 15. When we multiply the triangular numbers by 6 and add 1, we get the new sequence 7, 19, 37, 61. This is a sequence of hexagonal central numbers. We can visualize this sequence as single dot at the center and all dots forming hexagons, adding a new larger hexagon in each step. To understand better, the nth triangular number is the sum of the first 10 natural numbers. Multiplying this number by 6 gives n hexagons having 6 into 1, 6 into 2, 6 into n dots and a single dot at the center each time. So the n term of the sequence has 6 into 1 plus 6 into 2 plus 6 into n plus 1 dots. That is 6 into 1 plus 2 plus n plus 1 dots. 9. Consider the sequence of hexagonal centered numbers 1, 7, 19, 37, 61. We can form a new sequence by adding the terms of a sequence as 2, 3, 4, 5, 3 and so on. In this way, we get the sequence 2 cubes, 3 cubes, 4 cubes, 5 cubes, which is the sequence of cube numbers. We can visualize the formation of this sequence by adding the terms of the hexagonal centered numbers as shown below. In each of the figures, beginning from the second figure, you can very well imagine the visible dots equal in number to the newly added hexagonal centered number and the complete previous cube hidden inside, which has the same number of dots as the sum of the previous hexagonal centered numbers. For example, in the third figure, 19 dots are visible on the 3 visible faces. There are 3 invisible faces of this cube and the number of invisible dots is equal to the total number of dots in the previous figure, that is 1 plus 7 dots. Patterns in shapes. We observe various patterns in 1 minus 2 minus and 3 minus dimensional shapes. Some shape sequences are discussed below. 1. Number of sides in regular polygons. Regular polygons can be arranged in the sequence of an increasing number of sides. This sequence corresponds to the sequence of natural numbers beginning from 3. 2. The sequence of complete graphs. A complete graph is a simple graph in which every pair of distinct vertices is connected by a unique edge. The sequence of complete graphs is the pattern formed by the number of edges in the complete graphs where the number of vertices goes on increasing. This sequence corresponds to the square sequence of triangular numbers. Although the total number of edges in the nth figure is equal to the sum of the first and natural numbers. 3. Stack square sequence. We get the following sequence when we stack squares. The numbers of little squares that are joined together to form the various squares are in the sequence 1, 4, 9, 16, 25. This is the sequence of square numbers. Stacked triangle sequence. We will get the following sequence when we stack triangles. The numbers of up-facing little triangles form the sequence of triangular numbers 1, 3, 6, 10, 15. The numbers of both up-facing and down-facing little triangles combined form the sequence of square numbers 1, 4, 9, 16, 25. Notes 1. In each stack, the numbers of up-facing little triangles in various rows are in the sequence 1, 2, 3, 4, 5, that is the sequence of natural numbers. 2. In each stack, the numbers of up-facing and down-facing little triangles combined in various rows are in the sequence 1, 3, 5, 7, 9, that is the sequence of odd natural numbers. Gauss snowflake sequence. To form this sequence, we follow the steps. 1. We draw an equilateral triangle. 2. We draw an equilateral triangle in the middle of each side of a first equilateral triangle with with each new triangle pointing outwards. 3. To form each subsequent figure, we draw an equilateral triangle in the middle of each side of each equilateral triangle with each new triangle pointing outwards. 4. Erase the middle segment of each side of each equilateral triangle to get the sequence as shown below. In Gauss snowflake pattern or sequence, the number of line segments forming the figure becomes 4 times in each step.